Well, we'd like now to transition and, in the mid 2000s when we started to work with Dr. Crawley, who was yesterday's keynote speaker for with the ASHRAE group, we also started to work with the agroclimatology community. We found out that they needed solar irradiance, and so we have since started relationships and started supporting the agroclimatology researchers around the world. And one of those who has been foremost in using power products and in evaluating them and give us his feedback is Dr. Gerrit Hoogenboom, and a PhD from the Institute of Sustainable Food Systems. Dr. Hoogenboom is a preeminent scholar in the Food System Institute and professor of agriculture and biological engineering at the University of Florida in the United States. Prior to joining the University of Florida, he was director of the AgWeatherNet program and professor of agrometeorology at Washington State University. He has over 30 years of experience in the development of crop simulation models and decision support systems. Applications range from freeze forecasting to climate variability and climate change, water resources management, biofuels, economic and environmental sustainability, and food and nutrition security. He currently coordinates the development of decision support system for agri-technology transfer, DSS-SAT, and there's the website there, one of the most popular crop modeling systems across the world. He frequently organizes and facilitates international training workshops on crop modeling and decision support systems. He has published over 450 scientific papers in refereed journals, as well as numerous books and chapters and proceedings. Since 2019, he is the editor-in-chief of the journal Agricultural Society. He receives PhD from Auburn University, United States, Masters of Science and Theoretical Production Ecology, and Masters and Bachelors in Horticulture for Wageningen University in the Netherlands. Sorry about that, Gerrit. We're just so thankful that you take the time to make our presentation. Please feel free to use your 30 minutes. I know we're a little bit behind in time today. We're going to, you need to unmute and you're going to share your slides with us. So go ahead and do those things, and welcome, Gerrit. It's great to have you.
Thank you for the presentation, introduction here. So just to be sure, can you see my screen? Can you see my screen?
Yep, we can see your screen. Thank you.
Okay, good. Appreciate it. So apologies, I was not able to participate in the meeting yesterday. I was actually flying back from the Netherlands for a brief vacation. So I have quite a few slides with you to share today because I want to introduce you a little bit to the field of agriculture and how important weather is. But first of all, I'd like to recognize my co-authors who provided me with some material. Vijay Joshi, a postdoc in my program, Oscar Castillo-Romero, PhD student, Jeffrey White, a former USDA ARS scientist, and now working with me on a part-time basis, and Hudavadi Gurkan, a scientist from Turkey who was a former visitor in my lab. So I've titled subtitled my presentation, Agroclimatology from Station-Based Observations to Grid Data for Spatial Decision Support. So first of all, I want to show a little bit of a background about agriculture. For most of us, think about agriculture for food, for human consumption. But actually a large part of the agricultural production is used to produce feed, to feed our animals, which especially in the US and other areas of the globe is quite important. We use agriculture to produce our fiber for clothing. Somewhat controversial, but getting quite important as well. Agriculture being used for biofuel. And then, at least to enjoy life, we use flowers in horticulture and green industry, and actually was brought up in that area. You can also find agriculture and agroforestry more and more in bioplastics, pharmaceuticals, as well as other applications. So agriculture by itself is an extremely complex system that interacts with both what we call the biotic and abiotic factors. When we talk about the abiotic factors, of course, weather and climate are the most important ones. Look at the soil conditions with respect to water providing to the crop for water uptake and transpiration, nutrients. And we're looking at crop management. So these are the things the farmer can do with respect to his crop and variety selection, selecting when to plant, how dense to plant his crop, and what type of inputs to use. In addition, we also have biotic factors, which are a little bit more difficult to control, especially when we look at pests and diseases, where we have to apply chemicals, the same for weeds. And then what's happening in the soil, we sometimes refer to as the soil fauna. And then last but not least, agriculture at the end is not really about how much we can produce for a producer, but really it's about economics. So how much a farmer can gain with respect to the prices for his products and byproducts, what are the cost of his inputs and his labor cost. Unfortunately, he has to deal with policies, somewhat of cultural settings. And then also last but not least, which is very difficult for us to understand in the agriculture research sector, the human decision making. So what I saw in some of the previous presentation are tools and software that's being used in your industries are much less used currently in the agricultural sector, partially because farmers are still very much risk averse. And then on top of that, farmers have to deal with environmental constraints such as impacts and controls of pollution and limited availability of water. So when we look at weather and climate, agriculture, of course, is first of all driven by rainfall and precipitation for the rainfall production system. Temperature plays a major role in the crop production system. Solar radiation, and then when we talk about pests and diseases, relative humidity and dew point have a major factor. Soil temperature, the environment where the roots grow, and of course soil moisture. And to a lesser extent, when we talk about plants, atmospheric pressure is not important, but when we talk about livestock, atmospheric pressure also is associated with how the animals respond to the outside system. So the agricultural system as a whole is really exposed to many different facets of what's happening in the current century. We have to deal with food security, possibly not as much in the US and Canada, but if we look at the developing countries, food security is a major issue. In the agriculture sector, we have to deal with the climate risk, with climate change, climate variability, climate uncertainty. As I showed in my previous set of slides, also the increased demand for agricultural products. Consumers at the same time are also asking for improved product quality, with respect to both what the product looks like at the outside as well as the inside, the pressure on the natural resources and especially water availability for supplemental irrigation. And again, also rapid changes in technology. And at the end, really, there's a big gap between the information needed for decision making at different levels, going all the way from farmers to policymakers, and the lack of data that are available to make some of these decisions. So agriculture really is about uncertainty and risk. Here's a picture of flooding that happened in the United States in 2019, and currently what we see in the news is the flooding in Pakistan, where again are farmers affected by either extreme with respect to droughts and extremes with respect to water. In addition, we also have extremes with respect to temperatures as well, both at the high end and at the low end. So at the end, farming is really an extremely risky business. Farmer normally doesn't receive any economic and financial support for the governments. He has to deal with the weather variability on a day-to-day basis, on a seasonal basis. When you talk about large farm, also on a spatial basis as well. So the question really to bring up is, what are the sources of weather data, especially if you look at the United States, but also across the globe, that provide the data to make these decisions? So in the United States, we have the National Weather Service that provides us with the weather data, but most of these, again, are more generically based, not specifically geared towards the farmers. And in fact, if you look closely, most of the forecasts really are driven forecasts for the citizens. And secondly, we see federal aviation receiving forecasts from the National Weather Service. But other industries are normally of secondary importance. Now, when we look at the sources of weather data in the United States, we have what we call these cooperative weather station networks, where volunteers over many, many years have collected manually daily weather data, looking at maximum, minimum temperature, and precipitation. As an example here, this is one of the stations that was based at one of the sites where I worked as part of my career at the University of Georgia in Griffin, where data have been collocated since 1926. You see here what we call as a cotton shelter, but when I started, actually, you see the shelter in the center of the picture. Looks in a pretty bad shape, but this is the basic record of long-term weather data that are being used to determine climate change. And again, this is also the source of data that was available to make agricultural decisions. And a previous speaker's presentation, there was already some reference to the automated weather station that are managed by the National Weather Service. But most of these weather stations are really located at major airports, at least for agriculture, unfortunately. Agriculture is not conducted at these major airports. So we really have a challenge to look at the sources of the weather data. So that's why we see, at least in the United States and also in some other countries as well, that universities and colleges of agriculture have gotten into the business of actually installing their own weather stations. Because agriculture is conducted in remote locations, as I stated previously. Farmers need to have access to current weather conditions on a quite frequent basis. They need to have easy access to data, preferably free. And it needs to be reliable as well. So one of my first positions at the University of Georgia, although I'm a modeler by heart, I was actually tasked by the development of an automated weather station. So what you see here on the right of the picture is a traditional Campbell scientific weather station. The first one was installed in 1991, again at the location where I was working. Weather station network was called the Georgia Automated Environmental Monitoring Network, and at that time, as you can see in the center pictures, we actually used a dedicated landline to communicate with the weather station. And although it sounds easy to install one weather station, to actually develop a network is quite challenging because you need to select which sensors you're going to use, you need to select the sensor height, you need to look especially at quality control, you need to look at calibration, station maintenance, and communication. And all of this requires a fair amount of financial resources to maintain it. So with respect to the sensors, of course, these are the sensors I showed you, or the measurement I showed you earlier. So we're measuring air temperature at these stations, relative humidity, rainfall, soil temperature, different depths, wind speed and direction, and of course, solar radiation and some other variables as well. So again, the locations of these weather stations, what you see here in the red dots, this is the state of Georgia. And you see some in the pictures, the actual locations represent farms, represents research sites, represent universities. And actually you also see a very simple remote airport where we installed these weather stations as well. So the network grew from the first station in 1991 to about 80 stations in 2010 when I left the University of Georgia and moved to Washington State University. And luckily, the weather network is still operational as of today. With respect to robustness, this is a picture I obtained from one of my colleagues. So actually a tornado hit a site close by, but the weather station was still operational. And this is a picture of April 5th. So this is, again, not an advertisement for Campbell Scientific Weather Station, but again, they make very robust weather stations that can be used for remote monitoring. So I moved to Washington State University in 2010 to become the director of an AgWeatherNet program, actually a slightly larger network, like the largest network managed by land-grant university in the United States, with about 169 automated weather stations located across the state. So again, you can see the same weather variables being measured at this particular weather network as I showed you for the University of Georgia. Again, when we then look at the locations of these weather stations, it's quite different from when I showed you the map at the University of Georgia. You see a quite dense network in the center of the state is where most of the high-value crops are being grown, such as apples, cherries, grapes, and many other crops. You see some weather stations in the western part of the state, and in the eastern part of the state, where most of the wheat crops are being grown, see a lot less weather stations. Actually, managing this network and disseminating the data is still quite challenging. In one of my earlier slides, I showed you a dedicated landline, quite expensive, but luckily now with the use of cell phone technology, we're able to communicate with these weather stations at a much faster basis and also a lot cheaper. So basically, the data of these weather stations are downloaded on a 15-minute basis or more frequently, brought to a local server, and then also, which is very critical for agriculture applications, is to disseminate this information to the local users. But the weather dissemination is quite critical. When you talk to farmers and growers, they know what the local weather conditions are. They know what the temperature is. They know what the rainfall was. And they will remind you that you don't need these automated weather stations to make these decisions. So what is really key to be able to have a successful network and data dissemination system is a decision support system that allows farmers and other stakeholders to make more informed decisions using the local weather data. And ultimately, we want to get to actionable information that can be used in near real time. So one of the challenges farmers face in the area in Eastern Washington is where they grow a lot of tree fruit crops. As you can see here in the picture, is a crop of a cherry crop in full bloom. Is that these crops might bloom early and then there's a chance of a late frost. So they actually have invested in what they call wind machines to basically move the air and mix the air to make sure that the temperature doesn't drop below freezing. This is quite expensive undertaking. So what the farmers wanted in that case was actually a temperature alert that told them that the temperature would drop below a certain threshold value they could set. This message could be sent to their cell phone or to their email, whatever they were interested in. And then they would turn on the wind machine. So we need to be careful not having a false positive or false negative because of the tremendous amount of economic cost involved in making that decision. So this is a simple way of providing weather data support to the growers from a weather station. Now, another challenge these farmers face is with respect to how to grow a beautiful apple. So when you go to the store, you see these types of apples, but if you actually look at an apple tree on the left top, when it is in bloom, there are a tremendous amount of flowers on the tree. So the farmer is tasked to actually remove a large amount of flowers to make sure that the number of apples on the tree can be supported by the tree. And what they actually do is apply a chemical to kill the flowers, which doesn't make much sense to people not familiar with this type of production, but a farm is quite important. So what we actually had to develop was what we call an apple pollen tube growth model, a very precise model driven by temperature, including forecasts. And you can see some of the diagrams on the picture, but I don't really have time to explaining in detail. But based on this information and with the inclusion of the WRF weather forecast models, farmers could schedule when to grow into the orchard and actually apply the chemicals. So this is all very precise information, require very actionable information. So now I want to move over a little bit to a larger spatial scale using a dynamic crop simulation models. And Paul already in his introduction talked about the DSET system. So in our group, we're working with a fairly large group of people in the US and other centers across the globe on the development of dynamic crop simulation models that can only predict yield, but also predict crop growth development using weather data as input, using soil data again as input, using crop management, using genetics. So ultimately, these models will predict yield. If you look at the cost of production and the prices of the inputs, we can also look at net income. We look at environmental impacts, such as nitrogen leaching, and we can also look at resource use or irrigation management. So again, our software is not as sophisticated as the previous presentation. The system is called DSET. However, we do a fairly large community of users out there, mainly in the university system, somewhat in the private sector. So what we call an ecosystem of crop model users. We also train other trainers and model developers. And again, the system is based on an underlying crop simulation model with various databases around it. And again, the weather data and climate data play a key role in these crop simulation models. So ultimately, what we can predict is growth over time, as you can see here in this particular diagram. You see a day of year on the x-axis, which is January 1 as day 1, December 31st as day 365. The red line represents above ground biomass for the irrigated and rain-fed system for the green line, and the blue line is yield for rain-fed, and the black line, blue is for irrigated, and the black line is rain-fed system. So the continuous line is what the model predicts, and the points represent what we have observed on the field conditions. So these models are quite good in point-based predictions. However, one of the challenges we face when we talk about agriculture is really that agriculture is driven at more spatial basis. So we really need to look at bringing in spatial data with respect to these simulations. So with respect to that concept, this is where NASA Power come in and provide us with the spatial data for daily weather data and climate data to drive our crop simulation models together with spatial data for soil types, soil characteristics for crop management, and genotypes. So as Paul also mentioned, in early days, we've been involved, first of all, in the evaluation of the NASA product, especially for agriculture application, but also for some of the previous applications. We feel that from an academic perspective, it's very important that we evaluate a product we're working with. So in this particular case, we compare the data from these automated weather stations I showed you in the previous set of presentations with the NASA Power product. So what you see here on the left two maps is actually the correlation between daily weather station data of various weather station networks across the US. On the top left is for NASA Power. On the bottom left is what we sometimes use as called the weather generator, but we can see that NASA Power, of course, does a better job. On the right top, again, we see the NASA Power data for the difference between observed and simulated from the station data. On the bottom right, again, we see the weather generator data. So again, we can show here that the solar radiation data provided by NASA Power is a better data source than using my weather generator. And of course, we also need to look at the minimum and maximum temperature comparisons as well. In this case, we use the National Weather Service, the Climate Observatory Network. And again, here we see a comparison between the maximum and the minimum temperature data. On the left is Tmax, the bottom graph is Tmin. And then we use that information as an input into our crop simulation models. And again, if you compare the difference between NASA Power data, which is again the grid data versus the station data, our simulations were quite reasonable with respect to the predictions. And again, it depends a little bit on our objectives, on what we're trying to predict. So more recently, we've done some more comparisons between specific weather stations. You see here on the left, the Griffin weather station, which was the first station I showed you in my earlier slide. Now we have a comparison between the daily data from 1996 and 2021. On the right, you see a site in Konya, Turkey, with the maximum temperature. And see when we look at the statistical analysis for maximum temperature here, root mean square error and R square are all quite reasonable. Again, depending on the objective, how you're using the data, this could be quite reasonable. Similar here for comparison between the minimum temperature data, again, root mean square error is quite unreasonable because, as we know, there's also an error associated even with the observed data. And again, the R square data is good as well. So honing in then on what was mentioned in the previous presentations as well, we also conducted a training workshop on the use of the DSAT crop simulation systems. So we present then the NASA Power as an alternate source, or at least solar radiation data, which in many cases is not available for many of our users across the globe. NASA Power also as a source of quality control data for spatial simulations. And we have been quite blessed that Paul and his team have been so generous that there's a special option available within the NASA Power website now that you can select ECASAT data, which is a DSAT compatible format for our crop models. And when you download the data, it becomes available then in this particular file format that can directly be ingested into our crop simulation models. Again, then the challenges we face is that we really need to make some of these processes more automated, because some of our crop simulation models are being used on a regular basis across space and time. So, and we have one of my graduate students who's now developed a tool in Python where we can automatically merge the NASA power data. We have another data source for precipitation data, because we find, again, for agriculture application, that NASA power is not as robust. So we're using now the CHIRPS weather data, precipitation data provided by the climate hazard group, merge that into, again, a product that we use in our crop simulation models. Again, this tool is being set up by providing a workflow where we merge the data with respect to NASA power and CHIRPS, and then add it to our existing data sets. And then again, it creates a DSET compatible format where we now have two sources of rainfall data, one using the NASA power and one using the CHIRPS data. And finally, I want to show you some applications on how we used, again, partially in a research setting, some of these crop sum models applications. So compared to the previous presentations, we're not as far as along with the NASA power data being used in for actual decision support. So the first case is a current project we actually have at the Department of Defense, where we're trying to estimate rice yield production in Senegal River Valley in West Africa. So you can see here some of the diagrams with respect to where Senegal is located and where the Senegal River Valley is located in the system. You can also see the period of the dry season and the wet season. So in this particular case, again, we're using various sources of data, but again, the core weather data are based on NASA power merged with the CHIRPS data, combined it with the soil data and the crop management data. So in this particular case, we're first of all trying to provide in-season yield forecasting, where we run the crop simulation models on a spatial basis up to the days that the NASA power data are being updated, and for the remainder of the season, we use long-term historical weather data, again, from the our database. And then bringing that in a gridded database, you can see here an example of a gridded yield forecast that we conducted on March 29 for that particular basin. You can see the actual yield is represented by the size of the dots. So the bigger the dots, the higher the yield. And the variation is shown here based on the color of the size. So the yield range here for the forecast for August, September, based on the March prediction, ranges from 5 tons to 7 tons kilograms per hectare. So again, here we see then an example of the forecast on July the 1. We now try to aggregate the yield up to the region, because this is really what policymakers are interested in. We have 3 different regions here. We can see the average yield we predict, as well as the average yield for the entire region as well. Now, the second part we're also interested in is actually trying to predict when the crop will be mature. And with the models, we can also predict the rice maturity date for the rice crop and the harvest progression. In this, again, we do basically use a similar type of information, again, using the weather conditions and the weather outlooks using the historical weather data. We use the planting dates, which we obtain from flooding conditions from remote sensing. And then here we show a comparison between what we can do with the DSET model, where we can predict the harvested areas, where the dots, the orange dots are DSET predicted total area, and the blue dots represent a local official source called SIAD. So again, we can see that the crop models, we can do a fairly good job in predicting the area harvest progress over time. So rather than having to go into the field, you can use these crop simulation models combined with remote sensing data and the NASA power data to make those decisions and provide that information to local governments. And then finally, I want to show you a use case, again, for Ethiopia. There's not much information available, again, with respect to making yield estimates. One of the challenges Ethiopia faces for maize yield is a relatively low yielding crop. Inputs are very, very small. So you see here on the left top where Ethiopia is located. On the left bottom, you can see again the regions where maize is being grown. Again, we're using the NASA power data, merged with the chirps rainfall data, again, using the same soil weather database as input as well, local soil information. Then we're using, in this case, long-term historical weather data from 1984 to 2018, again, from NASA power, to look at a comparison between the baseline yield using Yo input for fertilizer, and then look in the impact when it would be an intervention by providing a subsidy so that farmers could actually apply an additional 50 kgs of nitrogen per hectare. So we can see the differences between the left top map and the baseline and the right top, which is the supplemental with respect to fertilizer input, and the map on the bottom shows you the actual differences predicted. So again, this information is being used by the Ministry of Agriculture in Ethiopia to help them make intervention decisions. So then to summarize, with respect to agriculture, this is the most important factor that really controls crop production at the end. So for farmers to make accurate decisions, for policymakers accurate decisions, we do need to have access to local automated weather stations, but the challenges are that these stations are very expensive, and really the information in the real world is not readily available. So for larger spatial scale applications, these weather stations are insufficient. In that case, then our power data provide us with a unique opportunity to scale up these crop simulations from a point-based simulation to a spatial simulation. And we really, as a crop modeling community, have benefited by the services provided by NASA Power. What we actually would like to see, though, is a higher spatial resolution because of the variability of agriculture across the landscape. We also would like to see a better quality product as well with respect to precipitation. So now finally, I really appreciate the support provided by Dr. Paul Stackhouse and his team. They've been very flexible at being able to communicate with us in allowing us to have a special format for what we call the castle format, which can be used for crop simulation models. And I know that my colleagues in the crop modeling community use this resource quite extensively, maybe not as extensively in the previous presentations, but I know that it is being used by users across the globe. So again, I really appreciate the opportunity to share my experience using the NASA Power data and also to show you the benefits of the tools. You can see here some of the sources of the weather data we've used in these comparisons, as well as access to these set software tool. So again, thank you so much.
Thank you, Gerrit. Wonderful presentation. Really enjoyed it. I noticed you took advantage of the long time series, 34 years. Is the time series, do you have a like a limit to the time series that you're interested in, or would you basically, if we had 40 years, you would take 40 years? Do you also look at like any changes, variability within that climate zone system growing area in terms of, you know, any sort of trends that you see? I'm just curious if you try to take those into account too, and how they affect the various growing seasons.
So the reason we normally recommend that our users use at least 30 years of data, because it goes back to climatology, where the normals are based on 30 years of data. But really, we like to use a time series that is as long as possible, really, to deal with the climate extremes and the weather extremes that could occur during that period. So
Okay.
we're not taking looking at climate change, and we know that climate change is happening, but we assume that weather tomorrow, when there's no accurate weather forecast available, has occurred in the past. So that's why we use these long-term weather series as input into our crop simulation models.